In this video on understanding dilution, you will learn about what it means to prepare a diluted solution from an original, more concentrated one. The objective is to help you gain a deep understanding of the concept of dilution and to learn how to apply the common formulas used in calculations. We will then go over word problems and you will learn how to solve them by applying those formulas. Finally, you will be given several practice problems which you can work on independently and then check your answers with the ones provided. We are all familiar with the concept of dilution. We take frozen orange concentrate and add water to it. We take a strong cup of tea and pour in water to make it weaker. And we prepare a strong vegetable and chicken stock to use later in cooking. In a laboratory, a similar process is carried out, but in a more precise manner. The chemist weighs out a certain amount of solute and dissolves it in a certain amount of solvent, most often water. This solution is called the stock solution and will be used as needed to prepare other less concentrated solutions. Having a stock solution on hand eliminates the step of each time having to bring out the solute, measuring it, and dissolving it. Of course, the chemist must make sure that the original stock solution is stable and that it does not lose its quality and characteristics while kept on the shelf. To prepare a diluted solution, the chemist will start with the stock solution. For visual purposes, let's make visible the dissolved solute. A suitable vessel is used for mixing, and a calculated amount of stock solution is placed into it. Note that the concentration in both vessels is the same. A solvent is then added. Notice that as the solvent is added and as the volume of the solution we are preparing increases, the amount of solute remains the same, creating a diluted solution with a lower concentration. Let's refer to the concentration formula to visualize this inverse relationship between volume and concentration. If the amount of solute remains constant, increasing the volume of a solution by adding a solvent will decrease its concentration. This visual nicely defines the concept of dilution. Dilution is the process by which concentration is decreased by increasing the volume of a solution while maintaining a constant amount of solute. The formula used in calculations involving dilution takes into account the relationship of four variables: C1, V1, C2, and V2. Once we are clear in our understanding of which variable refers to which aspect of the diluting process, the application of the formula becomes straightforward. In the formula, the number 1 refers to information about the stock solution. That is, the original, more concentrated solution. So C1 is the variable that represents the concentration of the stock solution, which can be called solution 1. A mixing vessel will be used to prepare the diluted solution, and a specific volume V1 is poured into it. Note that the concentration of the solution in the mixing vessel has not yet changed, and that its volume is that same amount that had been removed from the original container. To this volume, is added a certain amount of solvent, producing a new solution called solution 2, with a total volume of V2 and a final concentration of C2. The relationship among the four variables is represented by the mathematical formula C1 times V1 is equal to C2 times V2. The fact that the amount of solvent added is not given as an individual variable is easily explained by the definition of V2. V2 consists of the combined volume from solution 1 and the solvent, thus eliminating the need to include a fifth variable in the formula. However, we will see later that there are cases where the volume of the solvent by itself does need more consideration. And here is a good place to mention that in most cases, particularly with the type of question that a beginner chemistry student will come across, the solvent will be water, and the solution is referred to as an aqueous solution. An important strategy to note is that even though conventionally the number 1 refers to the initial, more concentrated solution, and the number 2 refers to the final, more dilute solution, it really does not matter if you switch them. The formula works just as well as long as the concentration and volume of the one solution are correctly paired up, and the concentration and volume of the other solution are also correctly paired up. C1 times V1 is equal to C2 times V2 is more commonly shortened to C1 V1 is equal to C2 V2. A typical question that a student would encounter would give 3 of the variables and ask the student to solve for the 4th unknown variable. Best practice in such problem solving is to manipulate the formula, to isolate the unknown variable on the left-hand side of the equation, and finally to solve for the unknown by plugging in the given information. Proper manipulation gives the equation for solving for the individual variables C1, V1, C2, and V2. But mathematical manipulation often poses a challenge to some students, and when that's the case, they can use a hack or trick known as the triangle. The triangle helps rearrange the equation and to isolate the unknown without the need to go through the algebraic steps every time. This is how it works for C1 V1 equals C2 V2. The triangle is drawn with a T inside it, dividing it into 3 parts: top, bottom left, and bottom right. The variables on the left of the equal sign in the equation are placed on the top, and the variables on the right of the equal sign are split apart and placed on the bottom left and bottom right. To get the equation, the unknown variable is blocked, and the location of the other variables relative to each other determine whether they are multiplied or divided one by the other. Top and bottom means division, side by side means multiplication. So, to solve for C1 V1, we cover it in the triangle, and we get C1 V1 is equal to C2 times V2. To solve for C2, we cover it, and we get C2 is equal to C1 V1 divided by V2. And covering V2 gives V2 is equal to C1 V1 divided by C2. Note, however, that this triangle does not solve for C1 and V1. To do that, we must use a mathematical theorem that states that if A is equal to B, then B is equal to A. Therefore, if C1V1 is equal to C2V2, then C2V2 is equal to C1V1. And we can create a triangle for this equation that can be used to solve for C1 and V1. Cover C2V2 to give C2V2 is equal to C1 times V1. Cover C1 to give C1 is equal to C2V2 over V1. Cover V1 to give V1 is equal to C2V2 over C1. Using this hack, a student can easily isolate any of the 4 variables as required. We can now apply what we've learned to solve typical word problems. Solving word problems in science and math is essentially an exercise in the scientific method. A problem is presented, the student identifies the information that is given, pinpoints the unknown, and chooses the appropriate tool, i.e., the appropriate formula, to solve it. To facilitate the problem-solving process for students, I have systematized it into what I call the 10 steps technique. It is a structured, logical guide that, with practice, becomes the go-to method to solve any word problem involving formulas and calculations. Its beauty is that the student can begin the solving process without really understanding the question. But as the information is sequentially deciphered, the problem unfolds, and before long it is solved. Here are the 10 steps to solving word problems. Step 1. Circle all numbers and units in problem. Underline the unknown. Step 2. List numbers and units. Step 3. Place an equal sign to the left of each. Step 4. Write the symbol for the variable to the left of the equal sign. Step 5. Determine the unknown, write down its symbol, then equal sign, then question mark. In parentheses, write the specific unit as indicated in the problem. Step 6. Check units, make necessary conversions. Step 7. Write original formula. Step 8. Manipulate formula by placing unknown on the left-hand side of the equation. Use triangle if necessary. Step 9. Plug in numbers and units. Cancel where necessary. Step 10. Solve. Circle final answer. Once mastered, the 10-step technique can help you solve any word problem without much effort. And, as I had previously said, even without the need to really understand the question. However, if you are a visual person and you would prefer to see the story behind the question, a set of drawings also helps. In solving the word problems that follow, I will use visuals to help you understand the question, and then I will go through the problem-solving process using my sequential 10 steps. For the next set of questions, we'll take the previously described preparation of a diluted solution and turn it into various word problems solving for different variables. Problem 1. In a clean beaker, you pour 400 milliliters of the 50 gram per liter solution that you have prepared. And you add enough water to make a 500 milliliter solution. What is the concentration of your second solution? We'll use the 10-step technique to solve the problem. Step 1. Circle all numbers and units in problem, underline the unknown. Step 2. List numbers with units. Step 3. Place an equal sign to the left of each. Step 4. Write the symbol for the variable to the left of the equal sign. Milliliter is a unit of volume and gram per liter is a unit of concentration. Step 5. Determine the unknown. Write down its symbol, then equal sign, then question mark. In parentheses, write the specific unit as indicated in the problem. The unknown variable here is concentration, its symbol is C, and we're not asked for any specific unit. Step 6. Check units, make necessary conversions. Our units are okay, but we note there are 2 V's and 2 C's, and so we must differentiate them. Recall that it really does not make any difference in the calculations as long as the given information about a solution is correctly paired up. From the question, we see that 400 milliliters and 50 gram per liter go together, so we'll label them with a subscript of 1. And that 500 milliliters and the unknown concentration go together, so we'll give them a subscript of 2. Step 7. Write original formula. That is C1V1 is equal to C2V2. Step 8. Manipulate the formula by placing unknown on the left-hand side of the equation. Use triangle if necessary. We're solving for C2. Isolating C2 gives C2 is equal to C1V1 divided by V2. Step 9. Plug in numbers and units. Cancel where necessary. In the setup, the units, milliliters, cancel. Step 10. Solve. Circle final answer. We use the calculator to multiply 50 by 400 and divide by 500. This gives 40 for the number, and we are left with gram per liter as the unit. Circling the final answer gives the satisfaction that we have expressed the answer as a complete statement and that we're done.
Yay!
Problem 2. Here's another variation of the same problem. In a clean beaker, you pour 400 milliliters of a stock solution. And you add enough water to make a 500 milliliter solution whose concentration is 40 grams per liter. What is the concentration of your stock solution? We'll use the 10-step technique to solve the problem. Step 1. Circle all numbers and units in problem. Underline the unknown. Step 2. List numbers with units. Step 3. Place an equal sign to the left of each. Step 4. Write the symbol of the variable to the left of the equal sign. Milliliter is a unit of volume, and gram per liter is a unit of concentration. Step 5. Determine the unknown. Write down its symbol, then equal sign, then question mark. In parentheses, write the specific unit as indicated in the problem. Here the unknown variable is concentration. Its symbol is C, and we're not asked for any specific unit. Step 6. Check units, make necessary conversions. We don't need to make any conversions, but we do need to differentiate between the two V's and the two C's in the question. We see that 400 milliliters and the unknown go together, so we'll label them with a subscript of 1. And that 500 milliliters and 40 grams per liter go together, so we'll give them a subscript of 2. Step 7. Write the original formula. The original formula is C1V1 is equal to C2V2. Step 8. Manipulate the formula by placing the unknown on the left-hand side of the equation. Use triangle if necessary. We're solving for C1. Isolating C1 gives C1 is equal to C2V2 divided by V1. Step 9. Plug in numbers and units. Cancel where necessary. In the setup, we cancel ml. Step 10. Solve, circle final answer. The answer is C1 is equal to 50 grams per liter. And this makes perfect sense because this answer indicates that we had started off with a higher concentration of 50 grams per liter and diluted it to 40 grams per liter. You may have noticed that problem 2 was more or less a repeat of problem 1 with only one difference. In problem 1, we were solving for C2, and in problem 2, we were solving for C1. I did this intentionally to show that the problem-solving process is identical. No matter what the unknown is, the 10-step sequential technique leads you effortlessly to the answer. Problem 3. You want to prepare 500 milliliters of a 40 gram per liter solution from a 50 gram per liter stock solution. What volume of the stock solution would you need to use? Let's start the 10 steps to solving the problem. Step 1. Circle all numbers and units in problem. Underline the unknown. Step 2. List numbers with units. Step 3. Place an equal sign to the left of each. Step 4. Write the symbol for the variable to the left of the equal sign. Milliliter is a unit of volume, and gram per liter is a unit of concentration. Step 5. Determine the unknown. Write down its symbol, then equal sign, then question mark. In parentheses, write the specific unit as indicated in the problem. Here, the unknown variable is volume. Its symbol is V, and we're not asked for any specific unit. Step 6. Check units. Make necessary conversions. We don't need to make any conversions, but we do need to differentiate between the two V's and the two C's. In the question and in our diagram, we see that 50 grams per liter and the unknown volume go together, so we'll label them with a subscript of 1. And that 500 milliliters and 40 grams per liter go together, so we'll give them a subscript of 2. Step 7. Write original formula. That is, C1V1 is equal to C2V2. Step 8. Manipulate formula by placing unknown on the left-hand side of the equation. Use triangle if necessary. Step 9. Plug in numbers and units. Cancel where necessary. Step 10. Solve. Circle final answer. I had mentioned previously that as long as the proper pairing is done, switching the subscripts does not affect the outcome of the calculation, and I will briefly prove that here. We'll replace V2 by V1, C2 by C1, C1 by C2, and the unknown is now V2. We solve for V2, and we get the same answer as we had previously gotten for V1. In the introduction to the formula C1V1 is equal to C2V2, I commented on the absence of an individual variable to represent the amount of water added to a stock solution in order to dilute it. I explained that the reason for the absence is that in the formula, the variable V2 represents the total final volume, meaning that it already incorporates the initial volume from solution 1 and the amount of water added to it in order to dilute it. In other words, V2 represents the combined volume from solution 1 and the water. I also mentioned that in some questions, the volume of water is given as a separate measured variable, which means it warrants its own identity and that it requires special treatment during the problem-solving process. To give it that special treatment, we will recognize that V2 is equal to V1 plus VW, and then alter the C1V1 is equal to C2V2 formula through substitution to show that other variable for water. That is not to say that we must use a special formula to solve such problems, and indeed, most students and teachers do quite well without it. But I want to go over an elegant way to handle questions where the amount of water is given as an independent entity. If V2 is equal to V1 plus VW, then we can substitute that information into C1V1 is equal to C2V2 to get C1V1 is equal to C2 times V1 plus VW. Our goal here is to isolate VW, so we divide both sides of the equation by C2 and then subtract V1 from both sides. Finally, we switch the sides to give the equation the conventional form of having the variable we are solving for on the left-hand side. Obviously, you do not need to memorize this formula because it can be derived as needed. But again, for those of you who have come to rely on that trusty triangle to manipulate equations, there is always that hack you can turn to. However, you should note that a triangle will only take you part of the way in solving for VW, because these triangles, magical as they may be, cannot be used where formulas involve addition and subtraction. Nonetheless, we will take a look at how it works. We set up the triangle for the given equation. The operation of addition that is involved complicates matters, but only slightly. Because there is no part of the triangle that shows VW on its own, we are stuck with solving for V1 plus VW. This gives the final solution for VW. As expected, it is identical to what we had previously derived through the process of substitution and proper manipulation. Even if we flip the equation, we are faced with the same process of having to keep V1 plus VW together until the last step. No matter how you decide to isolate VW, the final equation may seem daunting, but in the end, if you persist with it, you will appreciate how it perfectly replicates the story behind the word problem. On the next two word problems, we will practice using this formula. But if you prefer not to use it, I will also show you a way around it. Problem 4. How much water do you need to add to 400 milliliters of a 50 gram per liter solution to make a solution whose concentration is 40 grams per liter? We'll use the 10-step technique to solve the problem. Circle all numbers and units in problem, underline the unknown. List all numbers with units. Place an equal sign to the left of each. Write the symbol for the variable to the left of the equal sign. ml is a volume unit and gram per liter is a concentration unit. Determine the unknown. Write down its symbol, then equal sign, then question mark. Check units. Make necessary conversions. Here the units do not need to be converted, but when we see more than one of the same variable, we need to differentiate them. The 400 milliliter and the 50 gram per liter go together, and we will give them a subscript of 1. 40 grams per liter is clearly the second diluted solution, so it gets a subscript of 2. And the unknown variable is the volume of water, which we will identify as VW. Then we write the original formula and substitute V1 plus VW for V2. We can use the triangle hack if we need help in isolating the unknown VW. Plug in numbers and units. Cancel where necessary. Solve and circle the final answer. As I had mentioned previously, we can circumvent the altered formula I showed you, and when we have VW in our list, we can simply solve for V2 or V1 as the case may be, and finally calculate VW. Here we will need to solve for V2 because V1 is given. Continuing with the 10 steps, we get V2 is equal to 500 milliliters. But we must note that this is not the final answer. We are looking for VW, and now we solve for it. Problem 5. You add 100 milliliters of water to 400 milliliters of a solution whose concentration is 50 grams per liter. What is the concentration of your final solution? Let's solve the problem. Step 1. Circle all numbers and units, underline the question. Step 2. List all numbers and units. Step 3. Write an equal sign to the left of each. Step 4. Write the symbol for the variable to the left of the equal sign. Milliliter is a unit of volume, and gram per liter is a unit of concentration. Step 5. Determine the unknown. Write down its symbol, then equal sign, then question mark. Step 6. Checklist. We need to differentiate between the two V's and the two C's. We note that as stated in the problem, the 100 ml is the volume of water added, so we label it as VW. And the 400 ml is the initial volume from the stock solution, so we label it as V1. The 400 milliliters goes with the 50 gram per liter concentration, so we label the 50 gram per liter as C1. The unknown variable will be C2. Step 7. Write the original formula. That is, C1V1 is equal to C2V2. To solve the formula the elegant way, we substitute V1 plus VW for V2. Step 8. Manipulate the formula by placing the unknown on the left-hand side of the equation. Use triangle if necessary. We use the triangle to solve for C2. This gives C2 is equal to C1V1 over V1 plus VW. Remember that V1 plus VW is the same as V2. Step 9. Plug in numbers and units. Cancel where necessary. Step 10. Solve and circle final answer. Doing it another way, we can solve for V2 at the start and use the conventional C1V1 is equal to C2V2 formula without substitution. Not surprisingly, we get the same answer. How you solve it is your choice.
Can I try now?
Yes, Joey, I have prepared 5 practice problems for you to try. When you see the prompts, pause the video. On paper, solve the problem using the 10-step technique, then click to resume the video and to check your answer. Practice problem 1. You are given 300 milliliters of a 5 gram per liter solution. You dilute it to 500 milliliters. What is its new concentration? Pause the video. On paper, solve the problem using the 10-step technique. Now check your answer. I hope you got C2 is equal to 3 grams per liter for your answer. Practice problem 2. What is the final volume of a solution that started as 345 milliliters of a 25 gram per liter solution and now has a concentration of 15 grams per liter? Pause the video. On paper, solve the problem using the 10-step technique. And finally, check your answer. The final volume is 575 milliliters. Practice problem 3. You start with 900 milliliters of a 25 gram per liter solution and you add 50 milliliters of water to it. What is its new concentration? Pause the video. On paper, solve the problem using the 10-step technique. Check your answer. The new concentration is 23.7 grams per liter. Practice problem 4. Your 250 milliliter glass of iced tea tastes too strong. You dilute it by adding 150 milliliters of water and end up with a concentration of 8 grams per liter. What was its original concentration? Pause the video. On paper, solve the problem using the 10-step technique. Check your answer. The original concentration was 12.8 grams per liter. Practice problem 5. How much water must be added to 1 liter of a 16 gram per liter solution in order to give it a concentration of 4 grams per liter? Pause the video. On paper, solve the problem using the 10-step technique. Check your answer. The volume of water to be added is 3 liters. Thank you for watching. This completes a very comprehensive lesson on dilution. Following the steps you've just learned will no doubt make you an expert.